Hi, this is the class for digital system. So today we're gonna see two-level circuit optimization. So for this two-level circuit optimization, we are using Cardinal map. So Cardinal map. So this is also called K-map. So using the K-map, we can reduce the number of gate. So it is also related to min terms, what we studied previously. So the map method provides a straightforward procedure for optimizing Boolean functions. Here, the meaning of the optimizing the Boolean function is that we can use the minimum number of Boolean functions or Boolean gate or Boolean variables. That's why we can minimize the map or we can minimize the logic in terms of the number of the gate. Okay. So using this Carnot map, you can use up to 4 variables. But it is also possible to use more than 5 variables. However, in that case, it's not easy to follow up by human being or human visual sensing because we will see some examples about that. So in Carnot map, we are using X, Y axis. So in that case, here we can see we can put some combinations. For example, suppose that we have two variables x and y. So we can put here 0, 0, 0, 1, 1, 0, 1, 1, and so forth. So in here, in horizontal line, we can also put 0, 0, 0, 1, 1, 0, and 1, 1, something like that. But then we can consider two different variables here, two different variables here. So entirely we can consider 4 different variables in this Carnot map. But if you have more than 4 variables, then in that case, we have to put 3 different combinations here. We have to put the combination of 3 variables. So in that case, it will be very complicated in order to understand by human being. That's why we generally say that we are using Carnot map when we have up to 4 variables, not for more than 4 variables, okay? We're gonna see more details about that later. So here, as I told you before, we have we can put all kinds of possibility in one Boolean variable. So here we can put up all possible variances in another Boolean variable. Okay. So here in this map we have two different type of the variables. That's why we put x and y just like that. And in x we have two options, 0 and 1. In y we also have two options, 0 and 1. And in the case this is 400, this is 401, this is 410, this is 411 when we are thinking about x and y or something like that. So this is the map of these all possible combinations which can be generated by x and y. Okay, so here this is min term because this is talking about 0, 0. Then it means that this is x prime, y prime, or x bar and y bar. So in min term, x prime, y prime. So in min term, x should be 0, y should be 0 because x should be converted to 1 by this complement, and 0 should be 1 by this complement. That's why eventually we have 1 product 1, so we have 1 as a result. So this is the min term what we studied before. That's why here we can say that here this is x prime, y prime in terms of min term definition. So this is for 1, 0, 1, that's why this becomes x prime y. This is 1, 0, that's why 1 is x, 0 become 0 needs complement, that's why this become y prime. This is 1, 1, 1, that's why we don't need complement at all. That's why this is for x and y. So eventually we can make any kinds of min term definitions based on this Carnot map. Okay, that's why we studied about min term in our previous class. So here we will gonna see why we have to minimize the number of the gate because it has cost. So there are several definitions about the cost. So here we will gonna see what is the literal cost. Literal cost means the number of variables in this given notation. So here we have 1, 2, 3, 4, 5 Boolean variables. That's why we have 5. So our literal cost is 5. So here we have 6 different literal costs. 1, 2, 3, 4, 5, 6. That's why we have 6 here. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8. That's why we have 8 number of different literal costs. Here we have 1, 2, 3, 4, 5, 6, 7, 8. That's why we also have 8 literal costs. Okay. So we have another definitions in terms of the cost. That's why we have term cost, we have complement cost. So here, this example was taken from this example 1.2. So here we have literal cost as 8 and 8, what as we saw in previous slide. So in this case, we have to consider the term cost. So here we have two mean terms. That's why term cost is 2. Here we have 4 different max terms. That's why we have 4 term cost. So here we also have a complement cost. So we have 1, 2, 3, 4, 4 different complement. That's why we have 4 number of complement cost. So here in G2, G sub 2, we also have 4 different complement cost. So A prime, B prime, C prime, and D prime. That's why we have 4 different number of complement cost. Okay, that's why we have different number of different number of entire cost in this case. So here we will gonna see another examples for logic gate. So in this case, this is for XOR. Okay, XOR means that we have these kinds of min term. We also have this kinds of min term, and then we are doing the union. Okay, so then we can have this result. This is called XOR, and we can denote this XOR as just like this one. Okay, so based on this calculation procedure, we can get this result. So if they are same to each other, then we'll get 0. If they are not same to each other, then we'll get 1. Okay, so this is called XOR. XOR is the variance of the OR notation. That's why we're gonna have this one at first, and we're gonna have this one. Then it can say that this is XOR. So when we have this one in front of XOR, then we're gonna get the complement of all the results. That's why we're gonna get the complement of the result of the XOR. Okay, so this is called XNOR. So in this case, we are doing the product of X and W and X at first. We are doing the AND gate operation with Y and G, and then we're gonna see the union operation or OR operation. That's why we have plus. Lastly, we have the complement. That's why we have this one. Okay. So in this case, we have OR notation with W and X and another OR notation with Y and G. That's why we have this result. And then based on that, we have AND gate. That's why we have this one, product. And then finally, we have complement. That's why we have this one. Okay. So for the next one, they have the AND operation. That's why we have this one. They have AND operation. That's why we have this one. And then finally, based on the results, we have OR notation. That's why we have this one. Okay. In this case, we have OR notation with W and X. That's why we have this one. We have another OR notation with Y and G. That's why we have this one. And then finally, we have AND operation. That's why we have this one. Okay. So we can have these kinds of different types of the gate based on AND, OR, and complement. So here, we're gonna see the map reduce procedure. So actually, suppose that we have the logic gate equation that is called G sub 1. We have another logic gate equation that is called G sub 2. So they should be same to each other. It means that their truth table results should be same to each other. However, we want to minimize the number of gate. Okay. For this purpose, we are using the K map or Carnot map. Okay. As I told you before, we can draw Carnot map just like that. So in this case, as you can see here, we have 3 different Boolean variables. So x can be 0 and 1. That's why we have 0 and 1 in x. Here, this is the case where x is true because x is 1. Okay. On this vertical line, this is horizontal. In this horizontal line, we have y and g, 2 variables. That's why we have 2 different combinations. Okay. So 0, 0, which means that this is x prime, g prime because of the definition of the minterms. Okay. So in this case, y prime g. That's why we have this one. This is the case where y and g. This is case of the y and g prime. So in this case, in these 2 cases, y are true, 1. Okay, that's why this is combined with y. And in this case, the g are 1. Then in the case in this range, g is true. That's why we can make a segment just like that. Okay. So this is the case y is true. This is case g is true. This is the case x is true. Okay. So in the case, suppose that. So in that case, let's look at this space. Okay. This space is that x is not 1. X is 0. That's why this is x complement. So this case is the case where y is 1, g is 0. That's why y and g prime. So this is the case where x prime, g, y prime, g prime. Okay. So when you compare this one, so when you want to do the union or summation of these two spaces. So in that case, you can see that this is the same to each other. G prime is same to each other. The other thing they are not same to each other is the y and y prime. So in this case, when you want to combine both of them, then you're gonna have y prime, x prime y g prime plus x prime y prime g prime. Then you can combine with the x prime g prime and y plus y prime. This becomes 1. That's why this is eventually x prime and g prime. That's why you have this one, x prime g prime. Okay. So for this black box, you have another box here. For this black box, so in this case, your x is not 1. So this is x prime and y is true here in this range. That's why you can use the y directly, and that's it. Okay. So when you are using the mean-term definition, you're gonna calculate this one at first, and then you're gonna calculate this one at first, and you are going to do the OR notation. However, based on this map structure, you can easily see that you can reduce the term just like that. Okay. So in this example as well, we are adding two mean terms. However, we can use only this one. So as you can see here, you can reduce the cost. We already checked that the cost consists of literal cost, term cost, and complement cost. As you can see here, this has much less cost than this one. Okay, this one has a much less number of literal cost. This has much less cost in terms of the term cost. This has much less cost in terms of the complement cost. That's why this is much better. Okay, in terms of the logic gate design. So this is another Carnot map. So here we have 4 different variables. Wx, yg. So as we saw in the first slide here, we can have up to 4 variables. This is y. Okay, this is y. So if you have more than 4, for example 5 and 6, then we have to make this one much more larger. So in that case, it's not too easy to follow by our human eyes. That's why we use Carnot map up to 4 variables. Okay. So in this case, y and x, that's why this is the case where everything is 0. It means that we have to do complement for every single Boolean variable. That's why we have w prime, x prime, y prime, and g prime. Okay. So let's look at the other one, this case. This is 0, 1, 1, 1, okay? Because 0, 1, and 1, 1. So this is w, x, y, g. Y should be complemented. That's w should be complement. That's why w prime, x, y, g. So this place is for this one, okay? So we can draw all kinds of mean terms based on this Carnot map. And then once we are done, then we can combine. And we can make it much more simpler, okay? So let's look at this one. So this is one example about that. X should be complemented. That's why we are not looking at this one. We look at this one. We have to take the y is equals to 1, g equals to 1. X should be 0. So we have to take this one, okay? So in this case, y is 0, x is 1, g is complemented. That's why this should be 0. So we have to find 0 and 1 and 0. That's why this one. And then you can easily see that we can combine this one as 1, just like that. So here you can also check that this is the case where x is not 1, and then this is entirely for y itself. That's why you can use this, you can reduce this one into this one, okay? So this is another example. You have to see everything is complement in terms of w, x, y, g. That's why you have to take this one. And this is the case where w is 1, y is 0, x is 0, y is 0, and g is 0. That's why you have to look at this space. So in this case, w is 0, x is 0, y is 1, g is 0. That's why you have to look at this one. In the last case, you have to take 1, 0, 1, 0. That's why you have to take this one. And then you can combine. So when you wrap this one, when you make this one just like that, then you can take this one as 1. That's why in the case, you can see that this is the case where they are not in G. So this is the case where you have G. That's why these are all for G complement. So in this case, this is for X, as you can see here. That's why the other parts are for X complement. That's why our interesting area are for X prime and G prime. That's why we have final results just like that. Okay. So let's look at another example. you have this min terms. So min term says that we are interested in 0, 1, and 3. That's why this is 0, 1, 2, 3. It means that we have interest in 0, 1, and 3. Okay, not 2. So in this case, you have this Carnot map. So in this case, A complement and B complement. So this is the case where you have A complement and B complement. So here, this case is for A complement and B. So this area. The last case is the case where A and B. That's why you have interest on this area. So eventually we can check that you have interested in these areas, okay? So in that case, you can say that this is the case where you have A complement and A and B. So this one, okay? Or you can also say that this is B and A complement and B complement. That's why this is B plus A complement and B complement. Everything is fine, okay? Okay. But you can also think that in order to minimize the number of gate or Boolean variables, you can also think that, okay, we have interest in this area, so this is A prime. You also have interest in this area, this is B. That's why you can also write down A prime plus B. As you can see here, when you compare the literal cost, this one has 1, 2, 3 variable. That's why the literal cost is 3. So in that case, you have only 1, 2 literal cost. In addition to that, in terms of the complement cost, it has 2 complement. That's why it has 2 complement cost. It has only 1 complement cost. That's why it has 1 complement cost. So in terms of the cost, this is much better. Okay, this is much smaller. That's why this is much better. That's why it's better to use. Even the important thing is that even though this section is overlapped in the last case, that is fine. That is fine. There's no difference to each other. Okay, and then they are identical to each other. Okay. So this is better to use. So this is how you can reduce the map just like that. So the important thing is that you have to make this rectangle as large as possible. So in that case, you can minimize the number of the Boolean variables, because when you have larger rectangle, it means that you have a small number of Boolean functions, because when you have more and more Boolean variables, then you have more and more conditions. So when you have more and more conditions, so in the case you have more and more cost. That's why if you want to minimize the cost, then you have to use the little number of Boolean variable. That's why you have to make the rectangle as large as possible. Okay. So in the case you have larger 2 rectangles, and then even though they are overlapped to each other, that's fine. You don't need to worry about that at all. In terms of the logic, they are same to each other, okay? So let's look at the other case. This one, okay? So in this case, we are interested in this logic gate. So in this logic gate, let me look at the other example about this one. So in this case, M0, 1, 2, 3, 4, 5, okay, up to here, okay. So in this case, X complement, A complement, B complement, and C complement, this one. So in this case, A complement, B complement, and C, that's why this one. In this case, A complement, C complement, and B, that's why this one. In this case, A complement, B, C, that's why this one, okay. In this case, A and B, C complement, that's why this one. In this case, A, C, and B complement. A and C and B complement, this one, okay? So here, I told you that you have to make the rectangles as bigger as possible. That's why you have this rectangle at first. And then since this is very big, and you can say that this is just B complement. Okay? So this is B, that's why this is B complement. So you have the B complement. In addition to that, you can see this rectangle. Okay? Then these 2 rectangles are covering all our interesting area. Okay? So this one, just to say that this one just can be defined as A complement, because this is A, that's why this is A complement. That's why you have this result. Okay? So here, you have 0, 2, 4, 5, 6. Okay. So 0 means complement, complement, complement. So here. So here 0, 1, 0, 0, 1, 0 here. So here you have 1, 0, 0, 1, 0, 0 here. So here you have 1, 0, 1, 1, 0, 1 here. So lastly you have 1, 1, 0, 1, 1, 0 here. Okay. So you can see that here you have this one. This is C complement. So this is C, that's why these areas are for C complement. That's why you have this one at first. And then you have to consider this one. Then you can may write down this one as A, B complement and C, but now you are using 3 Boolean variables. This is not good at all. That's why it's better to use this one, even though we have overlaps, because it only has A and B complement. We do not need to consider C anymore, okay? Because it then in this case, this is much more better because it has less number of Boolean variable, okay? That's why you have A, B prime. For the next case, you have this one, okay? So in this case, you have 1, 3, 4, 5, and 6. 1 is 0, 1, 1, 0, 0, 1. 3 is 0, 1, 1. 0, 1, 1. And 4 is 1, 0, 0, 1, 0, 0. And 5 is 1, 0, 1, this one. 6 is 1, 1, 0, this one, okay? So then, in this case, you may think that you need this one, and then you need this one, you need this one, finally you need this one, okay? You have 4 different min terms. So for the first one, you have this one, you have A complement and C. A complement and C. So this one is the case where you have B complement and C. B complement and C. This one is the case where you have A and B complement. So the last one, this one, you have A and C complement. That's why this one. But eventually you can think that this one is overlapped by this one and this one. That's why you don't need to think about this one because it is already covered by this one and this one. That's why you don't need to worry about B complement and C. That's why you don't need to worry about this one. Okay. So finally you only have this one. Okay. You only have this one. That's why, because this area is already covered by this one and this one. That's why you don't need to worry about this one anymore. So let me look at the other one, the other cardinal map. So here we have typo. So we don't have 3 anymore. Okay. So here you have, so when you draw this one, so in this case, our truth table is very big. That's why we omitted the truth table. So eventually, when you look at this one, 0, 1, 2, and so forth, that is indexed by 0, 1, 2, 3, and so forth. That's why we just omitted the truth table and we just write down this one, okay? So here we have 0, 1, we don't have 3. We don't have 3. We don't have 1, 2, 3, 4, 5, 6. We don't have 7, 8, 9, 10, 11. We don't have 11, 12, 13, 14, 15. So we don't have these ones. The others are all our interest. So in that case, we can easily see that. We are taking this one fully. So this is C complement. That's why we have C complement at first. And then we have this one. Let me draw with this color. And then we have this one. Okay. Even though they are overlapped, that's fine. We can minimize the number of Boolean functions. That's fine. So in this case, this is D complement and A complement. Okay. So we have A complement and D complement. Lastly, we have to consider this one. Okay. But in that case, we are taking this area by this one, because we have to make the rectangle as larger as possible. So in that case, we can say that this is for the case where we have D complement and B complement. Okay, that's why we have this one. Okay. So let me look at the other one, the last one maybe. So you need a lot of exercise because you want to make, you need to get some insight which you can make the rectangle as large as possible. Okay. So you have A prime, C prime, D prime, A prime. So here C prime and D prime here. So that's why I made this one, okay? And A prime and D prime, A prime and D prime, maybe this one and this one, okay? A prime and D, not D prime, okay? So let me start from the first again, okay? So A prime, C prime, and D prime. So here, and then now you have A prime and D, A prime and D. So now B prime and C, B prime and C. So this one and this one, okay? And C and D, C and D. So now you have this one, okay? So A, B prime, A and B prime here, and D prime here and here, okay? So now finally you can see that you have the area of this one, right? So now in my case, I would like to do this one. So this is B prime and D prime. And then we have this one. This is C and D. Okay? Now you have this one. And this is A prime and C prime. Okay? So you are done. So by using, so then from here, let's check the number of literal cost. Literal cost is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You need time cost. Time cost, you have 1, 2, 3, 4, 5. You have complement cost 1, 2, 3, 4, 5, 6, 7. Complement cost 7. Okay, entirely your cost will be 24. So here your literal cost will be 1, 2, 3, 4, 5, 6. Your time cost will be 3 because you have 1, 2, 3 terms, and then your complement cost will be 1, 2, 3, 4. So finally your cost is 13. So your cost is much smaller than this one. That's why this is much better. Okay, that's why you can try this one. So this is the end of class today. So during this week, I would like to post 1 or 2 more videos in order to catch up our class schedule. So you don't need to worry about too much. Okay, thank you so much, and let's meet together again fairly soon.